Here's another example of finding whether a infinite series converges or diverges. In this one, we're going to also use the integral test, and so this one's a rather lengthy problem by the function that's involved. So the first thing we got to come up with is what does this infinite series look like? So we'd like to start our infinite series at 1. And so if we do ln of n plus 1 over the square root of n plus 1, that's going to match what this infinite series is doing. So we're going to take a look at its corresponding function, which will be the ln of x plus 1 over the square root of x plus 1. And this function is going to be positive as long as this is greater, x plus 1 is greater than 1, so that's certainly fine if we're looking at doing this from 1 to infinity to meet the conditions for the integral test. We'll be fine with that. The other thing is we need to be positive, so that is the positive, and then we need to be continuous and decreasing. This is a continuous function over a continuous function where the natural log is discontinuous, and well, the point where we're going to have problems is -1, which is not in the domain of either one. So this is continuous on its domain. Now we're going to go ahead and take the derivative of this thing. So the derivative of this thing is going to be a little bit lengthy. So we're going to do the quotient rule. And we'll go ahead and write a user-friendly rational exponent. So there's low, and then there's d high, 1 over x plus 1, minus the high function, and then derivative of low will be 1/2, and then subtract 1 from your exponent, all over the low squared, okay? And so the first order of business is, okay, well, I got x plus 1 to the 1/2, and then that's divided by x plus 1, okay? So we'll subtract the exponents, and we'll be left with an x plus 1 to the minus 1/2 here, okay? So x plus 1 to the minus 1/2. So that's the first thing that's going to happen here, and that x plus 1 to the minus 1/2 is going to match the second term that we have there. Okay, so we're going to have x plus 1 to the minus 1/2 power minus 1/2 x plus 1 to the minus 1/2 power, natural log of x plus 1 all over x plus 1. We'll go ahead and factor out the 1/2 and the x plus 1 to the negative 1/2, leaving us with 2 minus the natural log of x plus 1, and then that's all over x plus 1, okay? So we're going to go ahead and send the 1/2 and that negative exponent down to the denominator there. So who's left is 2 minus the natural log of x plus 1 on the top, and then on the bottom there's the 2 from the 1/2, and then x plus 1 to the 3/2 power, okay? And we want to know when is this thing negative, okay? Now with the integral test we have some flexibility. It doesn't necessarily have to start decreasing at 1. It's just it eventually needs to start decreasing for the rest of time. So the top is where we're going to change signs. The bottom is always going to be positive. So we're going to be looking at when 2 minus the natural log of x plus 1, when is that less than 0? Well, that's when 2 is less than natural log of x plus 1. Because the exponential function e is increasing, we can go ahead and apply e to both sides, and we'll have e squared is equal to x plus 1, we'll subtract 1, and so we have e squared minus 1 is less than x. So as long as x is past e squared minus 1, this function is going to be decreasing. So we're unable to apply the integral test for the first couple of terms, whatever e squared minus 1 is, 3 or 4. I don't know. Use your calculator to find it. So let's say it's conservative estimate. Let's say that this is 6. It's definitely not 6, but let's say it is 6. That means we can't use the integral test for the first 6 terms of the series, okay? And the first 6 terms, that's finite. That's not going to affect whether it converges or diverges. So we're okay with that as long as it's eventually decreasing. So that's okay. So we have the we got the decreasing that we want. So maybe it's not starting at 1. That's okay. That's not a problem. It's decreasing for the rest of the time after at least 6. Okay. So that allows us to go ahead and look at the integral, the improper integral. Oh, it looks like I wrote good enough over my decreasing here, so that's good enough. Anyways, so let's go ahead and look at our integral. Improper integral from 1 to infinity of the natural log of x plus 1 over x, the square root of x plus 1. And, oh, yep, you guessed it, we got to do integration by parts. So we're going to let u be the natural log of x plus 1. And du will be 1 over x plus 1 dx. dv will be the square root of x plus 1 on the denominator, so we'll write that a little bit more user-friendly with the rational exponent. And then v will be 2x plus 1 to the 1/2 power. So I'm just going to go ahead and not worry about the improper integral. We're just going to go ahead and find the antiderivative, and then we'll incorporate in the improper integral stuff in a moment here. All right, so natural log of x plus 1 over the square root of x plus 1 dx, well, that's going to be your ultraviolet voodoo doctor, so uv, I've done vu, order does not matter, and then minus v du. So when I say the order doesn't matter, I mean I can do uv or I can do vu. I don't mean that we can change this order and this order here. So then minus the integral of v du, and we can go ahead and factor out the 2 there out of the integral, okay? And we got some nice stuff going on here. That's an exponent of 1, so this integrand is going to become x plus 1 to the minus 1/2. So we still have all that stuff out in front. ln, whatever all that mess is. Minus 2 integral of x plus 1 to the minus 1/2 dx. Okay, so then we'll go ahead and find the antiderivative of that. And so that's just a simple power rule, okay? And so then we have the antiderivative of that. But wait, there's more. We're not done. So we found the antiderivative. Now we got to install that and use that in the improper integral here. I went ahead and factored out the x plus 1 to the 1/2 power just to make it a little bit cleaner. Okay, so that's what we got going on there. That's our antiderivative. 2x plus 1 to the 1/2 power times the quantity ln of x plus 1 minus 2 plus constant of integration. Just terrific looking antiderivative. Now let's go ahead and go on to one more slide, and we'll go ahead and put that all together. So the improper integral of ln of x plus 1 divided by the square root of x plus 1 dx is equal to the limit as b goes to infinity of 2x plus 1 to the 1/2 power times natural log of x plus 1 minus 2, evaluated from 1 to b. I think I missed my parentheses here. I think I put them in a little bit later, but sometimes we get carried away in excitement, so I should have an additional parentheses there. And so we'll go ahead and evaluate that. So the limit as b goes to infinity, 2 times b plus 1 to the 1/2 power, natural log of b plus 1, minus 2, and then evaluate it at 1. And so when we evaluate this limit, that's going to infinity, that's going to infinity, this is constant, so our limit is going to be infinity. Okay, so that is infinity. So then that means that the improper integral diverges, and so by the integral test, the infinite series diverges also. So we have divergence by the integral test. Okay, so we got to have a lot of fun with this one. We didn't get to do L'Hopital's rule on this. Maybe there'll be another one where we get to use the L'Hopital's rule, but we got to throw in the integration by parts, and I think the previous one we got to play with the arctan. So it all finds its way in here when we're working through these problems. Okay, so long story short, we have a divergent infinite series here.